Today we are going to start a very important circuit known as the LCR circuit. In LCR circuit we are using three circuit elements: resistors, inductors and capacitor. We have to find out in this topic the phase relationship between current and voltage, and the second one the impedance. Impedance, as we know, that work to oppose the current flow in the circuit. So let us start. Suppose this is applied voltage across this LCR circuit, which is E is equal to E naught sin omega t, and we have three circuit element: resistors, inductors, and this is our inductor, and this is our capacitor C. We already know that when there is only one circuit element, that is the resistors, the phase relationship between resistors and current are in the same phase. Let us suppose this is our current, and the voltage across the resistor is VR. They are in the same directions. They are in the same directions because they are in the same phase. Similarly, if the current vector is along this one and our voltage across the inductors are ahead of the current by an angle of pi by 2. So this is our pi by 2 radians. So because voltage across the inductor are ahead that of the current, so this is our voltage across the inductor VL. Similarly, we know that in a capacitors, if current is along this one, our voltage applied across the capacitor will be just lagging behind the current by an angle of 90 degrees. So we have to rotate by an angle of pi by 2 in clockwise directions. So this is the phase relationship between current and voltage in resistors and in inductors and in capacitor. Let us find out the phase relationship as a whole. We already know that we are supposing current and voltage as phasor vectors. In phasor vectors, we are using the vector sum of additions of any vectors. So here the applied voltage E is equal to voltage across ER and plus voltage the net voltage E at some particular times will be the vector sum of all the vectors VR, VL and VC. Therefore, the resultant vectors at some particular time t E is equal to voltage across resistors plus voltage across inductors plus voltage across capacitors. So these are the vectors. We are calculating the resultant T by using the law of parallelograms. So here at any particular times, voltage across resistor is VR is equal to IR, and the voltage amplitude, the maximum voltage across the resistors would be V naught R is equal to maximum current into this. Similarly, the voltage at a particular time t across the inductor is equal to VL I into L, and the maximum voltage across this inductors becomes V maximum, I maximum, and the resistors of the inductor, that is XL. Similarly, voltage across the capacitor at a particular time t is equal to VC, which is I times XC. X is the capacitive reactance. So maximum voltage across the capacitors, we represent it like this: I naught XC. Here we already know that XL has the value omega L and XC known as like this omega C. So here now using law of parallelogram, by using law of parallelogram, we will be able to solve the sum of these three vectors. Now finding the resultant of applied voltage VR and plus VL plus VC. First draw the vectors I. Let us suppose I is along this one. The phasor is along this one. We already know that VR and I in the same directions, or we say that in the same phase. Therefore, this will be VR vectors. And here, if I is along this one, we know that the VL vectors is making an angle 90 degree with the current I in anti-clockwise direction. So this would be our VL, voltage across inductors. And similarly here, if the current is along these ones, and VC would be along downward directions, making an angles pi by 2 in clockwise direction. So here, if the current is along these ones, current vector is along these ones, and VC along the capacitor would be just clockwise direction, so making an angles 90 degree. This is another 90. So therefore VC becomes this one. So now here, if in magnitude there are two conditions. If VL, voltage across the inductor, is greater than voltage across the capacitors, then the vector additions, we know that the angles between VL and VC is 180 degree. Therefore, the resultant of VL and VC would be along VL minus VC in the direction of VL. Suppose the resultant of VL and VC would be along this one. Now this is the resultant of VL minus VC. This is vector VL and minus vector VC. So the resultant of VR and VL minus VC, by using the law of the parallelograms, we have make a parallelogram here, would be this. This is the vectors. So here, or we can say that if VL has the value I into XL greater than I times of, by using the Ohm's law, XC. So I would be cancelled out from here, XL greater than XC. In other case, we can say that because the current in all the circuit elements, resistors, inductors and capacitor is the same, so that's why the current is both VL and VC are the same. So we have cancelled out this one. So from here, XL greater than XC, it means that inductive reactance is greater than the capacitive reactance. So therefore, in such cases, the resultant of VL and VC would be along the direction of VL. This is our phasor diagrams of a series LCR circuit. Now using the law of parallelogram, this is our parallelogram. Resultant of VR, VL minus VC would be the applied voltage E. Therefore, it would be our applied voltage. So here, it is seen that this applied voltage already is ahead of the current. Let us suppose the angles between I and E is phi. And here in this terms, sin omega t making an angle omega t with the positive direction of this one. Therefore, if this applied voltage make an angle omega t with this, therefore the current voltage, this is the current voltage, will have an angle phi, omega t minus phi. This is your omega t, this is your phi, therefore the angles becomes omega t minus phi. So if your current voltage if I represent by I, which becomes I naught sine omega t minus phi, and our voltage at that instant will be E naught sine omega t. So this is we have find out with the help of the phasor diagram very easily. Now let us find out the resultant I naught, what the relation between I naught and E naught, and what would be the impedance of this LCR circuit. Impedance means the resistance of this LCR circuit. Okay, and like the resistance, normal resistance impair the flow of the current, likely the impedance we called impedance, the resistance of the circuits would also impaired, would also broken, would also obstruct the flow of the current in the LCR circuit. Let us find out by using the law of parallelogram. So here you can see that this makes a parallelogram, and in the parallelogram resultant of this is the resultant E vectors of VR and VL minus VC. So this is your vector VL minus VC, because VL has the magnitude this one, VC has the magnitude of this one, because they are making an angle 180 degree to each other. Therefore resultant of VL and VC will be VL minus VC, because they are antiparallels and the amplitude would be lesser than of VL. That means VL minus VC. Let us find out this with the help of the law of parallelograms. Yeah, using this right triangles. In right triangles, its amplitude is E naught. Amplitude means length. Amplitude is E naught whole square. Amplitude of the applied voltage, it means that E naught whole square is equal to, and here is voltage across this one, or voltage amplitude is V naught R whole square plus voltage across this vector. Across this vector we have VL minus VC. Its amplitude becomes, we write like this one, V naught L minus V naught L minus V naught C whole square. Now using this expression, using this value V naught R is equal to maximum value of the current into this, and similarly V naught L voltage amplitude across inductors is equal to I naught XL, and similarly voltage amplitude across capacitor is equal to I naught XC. If I put all these values in this expression, I will be able to find out I naught R whole square plus I naught XL minus I naught XC whole square. So now after getting I naught outside, and we will be able to find out the value of maximum current in terms of E naught and impedance of the circuit. If I calculate the value from here, E naught whole square is equal to I naught square times this plus I naught whole square is common from this expression inside of this ones, XL minus XC whole square, XL minus XC whole square, and finally take I naught squares common from both the terms, R square plus XL minus XC whole square. Now therefore I naught whole square becomes maximum amplitude whole square divided by R square plus XL minus XC whole square, and therefore I naught taking the square root both the side, E naught divided by R square resistance across the resistance plus the resultant reactance XL minus XC whole square. Now this value known as the impedance, we generally represent it by Z. Now the current, finally we have this value E naught divided by square root of R square plus square of XL minus minus XC whole square. Now this value becomes impedance X naught divided by Z. So this is the impedance, or I can say that the resistance of the LCR circuit. This is known as impedance or resistance of LCR circuit. Its value will be R square plus XL minus XC whole square. If I place the value of XL, this becomes square root of R square plus XL as the value omega L minus 1 upon omega C whole square. So this is the first case. In the first case I have written that VL here in this case voltage across the inductor is greater than voltage across the capacitor, therefore resultant will be along this one. So the resultant, this is the resultant of VL and VC, therefore resultant of VR, VL minus VC will be along this one. Here the voltage, this is the voltage, applied voltage across the LCR circuits is ahead of the current. Your current is along this one, ahead of the angles, ahead of the current by an angle of phi. And let us start in second case. In second case, when VC greater than VL, in that case resultant of VC and VL will be along this one, and resultant of VR, VL minus VC will be along this one. In that case your current will be ahead of the resultant voltage. Let us start. In the second case, when the voltage across capacitor is more than that of the inductors, what will be the resultant of these three vectors? We already know that the resultant of applied voltage is the resultant of voltage across resistors plus voltage across the inductor plus voltage across the capacitor. We have to find out resultant of these three vectors in the vector additions rule. So here let us start. First draw the current vector. We already know that current and voltage across the resistor are the same. Let us start first draw the figure. This is y-axis and this is your x-axis. First draw these vectors. I and V are in the same phase because they will be in the same direction. Let us start this, because normally the amplitude of the voltage across the resistor is more than that of the current. Let us start with your current, and it would be your voltage vector VR. And we already know that VL is ahead of I, so that's why it is ahead. We have drawn an angle pi by 2. VL is along an angles of pi by 2 in anti-clockwise direction. Therefore, this is making an angle 90 degree. We generally represent this square at this place, and this is your VL. Similarly, here current is ahead of the VC by an angle of pi by 2. So this is your current. We have drawn VC in anti-clockwise direction after rotating pi by 2 from the current vector. This is your current vector, this is your voltage vector. If this is your current vectors, rotate VC, this is your VC vectors by an angles of pi by 2 in anti-clockwise direction. That's why it would be your angles. So in this case, now the case is, if in this case is VC, because VC and VL are anti-parallel, means the angle between them, this is the angle between them, will be 180 degree. Let us start. So here VC, if VC greater than VL, we already know that VC has the value IXC greater than IXL. If I cancel out I, because in whole circuit current will be the same, and here we can also say that capacitive reactance should be greater than inductive reactance. So in this case, so this is the vectors, this is your VC, this is your VL, and VC minus VL has this magnitude. Therefore, this is the vectors VC minus VL have the magnitude lesser than VC. So resultant of this vector and this vector by rule of parallelograms will be along the diagonals. This is your diagonal. Yes. Let us suppose it makes an angles of omega t, because this applied voltage has an angles at the time of is omega t. Let us start this one. This is along x-axis making an angle omega t, and the phase angles between current and omega t we generally represent by an angles of phi. So this will be your phi, and the final angles, the current vector is along this one. This is your current vectors making an angles from here, this. Now this becomes omega t plus phi. So this is your omega t minus phi. So therefore your correspondings, if your applied voltage is sometimes is this one, your corresponding current vector becomes I naught sine omega t plus phi. So because this current vectors ahead of this voltage vector by an angle of phi, that's why its the phase angles of the applied voltage is omega t, and the phase angles of current vector becomes omega t plus phi. Now let us start how to find the impedance. Now using Pythagoras theorem, you know that its amplitude, length of this applied voltage E naught whole square. E naught whole square is equal to amplitude this vector, which will be amplitude across the resistor V naught whole square, and plus amplitude of this vector will be the same as that of this one. So therefore the amplitude of this one V naught C minus V naught L whole square. Now putting the value of V naught, which is I naught R whole square plus I naught XC minus I naught XL whole square. Taking I naught outside, it becomes I naught whole square R square plus taking I naught from here after making a square of this one, because it has whole square term. I naught square, if you bring something from the square term, it again becomes square. So I naught whole square inside of this one will be xc minus xl whole square. So from here, if I calculate the value I naught outside of this one, r square less xc minus xl whole square. So this is our impedance part. Now after calculating this one, I naught whole square is equal to the square of the applied voltage vector divided by r square plus xc minus xl whole square. After taking the square root, it becomes I naught E naught divided by r square plus xc minus xl whole square. Now this term will be impedance. This is impedance. We also write in this format. If I put the value of xc and xl, it becomes square of r less xc has the value 1 upon omega c minus 1 upon omega c known as capacitive reactance, and xc has the value omega L, which is inductive reactance whole square. Now we can write this one E naught upon Z. This Z has the known as impedance. This is the amplitude vectors. I can say that applied voltage, maximum applied voltage divided by the impedance. Impedance means resistance of LCR circuit. Therefore, I naught is equal to E naught divided by Z. Your Z has the value impedance. Now how to calculate the phi with the phasor diagram. It is our phasor diagram. This is your phasor diagrams. From here you can see that your current vector, this is your current vectors, and this is your applied voltage. The angle between them is phi, known as the phase angle. It is already seen that this current vector is ahead of the voltage vector by an angle of phi. Therefore, the relations is reflected here in this applied voltage and corresponding current. Now, this phi can be calculated by using the impedance triangle. This is your impedance triangles. Along this one will be the vectors VR. Along this one will be vectors VC minus VL. This is VC minus VL. The angle between them is 90 degree. This is your hypotenuse, known as the impedance. Angle with this by this vector making phi. This is known as the phase angle. So from here tan phi is equal to tan phi perpendicular divided by base. Your perpendicular is VC minus VL, VC minus VL divided by VR. If I put the value of uh, VC, VL and BR, it will be IXC minus IXL divided by I into R. After taking I common from here, it becomes I times of XC minus XL divided by I into R. After cancelling I, the value becomes XC minus XL divided by R. So from this impedance triangle, we will be able to find out 10 phi. We also, if I remove this one, we are in this one. So you already know that this is the resistance across the resistors, and this is the resistance known as XC minus XL. XC minus XL. So from here 10 phi become this one. Similarly, cos phi, power factor is also known as power factor. Later we will study about this power factor of this LCR circuit. As equal to, from here cos phi R divided by impedance. R divided by impedance, your impedance is equal to square of the resistance plus XC minus XL whole square. This is the power factors. We can easily calculate from this impedance triangle. This is your impedance triangle. Impedance triangle. So in this way, overall, we have using two cases of this LCR circuit. In first case, when VC greater than VL, and second case when VL greater than VC. First case VL greater than VC, in second case VC greater than VL. So only the difference is here. In 10 phi, here XC minus XL. In earlier case, it is XL minus XC divided by R. Now the topic is over.